All right, everybody, let's get started on the problem of the day you just handed in. A lot of this chapter relies... I can wait, you guys. I heard people talking, so I was going to let you finish. That was a joke. All right. This chapter relies very heavily on proton transfers and keeping track of your arrow pushing and charges. So I'm going to emphasize that in the next few problem of the days. You need to include all your charges and correct arrows. This one is very similar to what we saw last chapter, which is why I thought you guys could do it on your own. What do you think the first step's going to be? Protonation. So in this case, we are going to protonate our nitrile. We now have a positively charged nitrogen. The next step, what do you think that'll be? Well, it's equilibrium, so it's assumed it can go either direction, but what can drive this forward? We've got water around still. So this water can add into this carbon and dump electrons onto that nitrogen, right? So when we do this, we get what looks like an imine derivative. Oh, thank you. I am missing a carbon. Okay, so now we've got our imine derivative. We can deprotonate this with water to get the proton off of the oxygen. Turn that into an alcohol. I'll fill in my arrows here in a bit. And now we've recreated hydronium. What do you think the hydronium is going to do? Protonate the nitrogen. So in this case, we're just doing a proton transfer. Move electrons over. There's a couple different ways to show this, but this last sequence of steps was just a proton transfer from the water that added in onto the imine nitrogen. Now with this lone pair on this oxygen can dump down. Oh, I keep on missing my carbon. Sorry. So do you see the lone pair on this oxygen? Yes. Dump down to form a new double bond between it and the carbon. Okay. And then the double bond from the nitrogen, one set of electrons got dumped over onto that nitrogen, and so now it doesn't have a charge anymore. This nitrogen now has a lone pair on it. So this looks pretty close to an amide functionality, right? We just have a protonated carbonyl. This is done in aqueous acid, so this water can add in, dump up electrons. All right. And the next step will be another proton transfer. So we're going to deprotonate our alcohol. So this looks a lot like the hydrate that we saw from last chapter. All right, and we're almost there. This is a pretty steppy reaction. Now we've got hydronium around. This can get, or given a proton to the amine. Now we've got a great leaving group. So the oxygen can shove off the leaving group. We're left with, let me slide this over a bit. We're left with our precursor to our carboxylic acid plus ammonia. And our ammonia can come grab this proton and give us our carboxylic acid.
Isn't the ammonia a gas?
In this case, if it's in solution, it'll stay in solution. So if you ever buy Windex, you can actually smell ammonia in solution. All right, so we get our carboxylic acid plus the ammonium ion. Yeah?
What isn't the water exact the middle area?
This one? Oh, shoot. This one?
Why isn't the water attack there instead of making like aldehyde? Like, why couldn't you have the water attack the carbon?
You could, but then we'd be.
And then make a hydrate.
We can do that. As long as your sequence of protonation and deprotonation follows correct arrow pushing, that's fine too. I really, at this point, I want correct proton transfers. Whether or not it happens immediately before or immediately after a given step is somewhat trivial. I just want to make sure that you're doing protonations and deprotonations. Yep.
So if you have say instead of the standard group on the end for your starting material, you have I don't know, NH2.
Mm-hmm.
Can you use that? Can you use acid to create like a ketone or aldehyde? It's using the same mechanisms or different variations using the same type of mechanism stuff?
No, but the one thing I will say is that if you look at this group over here, this looks a lot like an amide, and you can hydrolyze amides into carboxylic acids. Amines you can't really convert very easily into a carbonyl group, but you can convert an amide into a carboxylic acid using this similar mechanism. All right, so let's continue on. In chapter 21, where we were finishing up yesterday talking about carboxylic acids, today we're going to move on to carboxylic acid derivatives. And so carboxylic acid derivatives I like to draw using a Z, where Z can be any sort of functional group. But the key thing with the derivative of a carboxylic acid is that they have the same oxidation state. And so in this case, usually it's going to be a +3 oxidation state. We're not gaining or losing electrons, we're just swapping out a functional group. So we've got a handful of different carboxylic acid derivatives. It's some substituent, and so I'll go through examples of what that Z substituent can be. Z is some sort of electron withdrawing substituent, though. So the first example is where you have a halogen on there. So X equals chlorine or bromine. What are these called?
Acyl.
Yeah, or acid halide. So this is a carboxylic acid derivative. Let's check our functional group memory bank here. What's this functional group? Anhydride. So in an acid halide, the Z group can be thought of as that X, and then in anhydride, it's this entire group can be thought of as that Z group. We've got another one. I'll be bummed if you guys don't know this one. What's this functional group? An ester. It's not an Easter. So we've got esters. And again, the Z group in this case is going to be the alcohol. And then last but not least, what's this functional group? Amide, amide, depending on what part of the world you're from. The British pronounce things funny. I don't know. They think they invented the language or something.
I mean, it is called English.
All right, so if we look at all the carboxylic acid derivatives, one thing I want to point out is that as we go up this trend, they're more reactive. And we're going to talk about this quite a bit more, but acid halides are more reactive than acid anhydrides, and they're more reactive than esters, and they're more reactive than amides. Amides are relatively unreactive compared to the remaining ones. All right, now we get to do my least favorite part, nomenclature, but we got to do it. We do. I don't like nomenclature, but like my old advisor used to say, we have nomenclature so that we don't point and grunt at things. So for acid halides, the suffix is going to change. The new suffix is going to end with -il. So you're going to replace oic acid with an -il, and then we're going to do bromide or chloride. So let's do some examples here. So let's compare this carboxylic acid versus its corresponding acid halide. What would the name of the carboxylic acid be? Yep, hexanoic acid. Versus, whoa, this should be a chloride. All right, so we're comparing the parent carboxylic acid to its derivative acid halide. So we're going to replace the oic acid portion, or sorry, the ic acid with the -il bromide or chloride. So in this case, we're going to name this compound hexanoyl chloride. Oh, thank you. Hexanoyl chloride. It sounds ugly, I know. So we're replacing the ic acid with the oil chloride. Let's do another one just to make sure we've got this. What's the name of the carboxylic acid? On the left? I heard it. Acetic acid. Which means that this... Whoop. What? No, it's acetic. Oh, you're talking about the other name. Oh my gosh, guys. Acetyl chloride. So we're replacing the ic acid with the -il chloride. And that's more or less how it goes for naming all of our acid halides. All right, now let's go back to a different functional group. Let's go to anhydrides. Anhydrides, we're going to just add on a new suffix, and it's going to end in anhydride.
Oh, that's clever.
Yep. pretty simple naming system. So let's explain this with examples. Let's go to a little bit of a different one. Actually, let's stick with acetic acid. We'll do the harder one next. So we're going to replace the acid portion with anhydride. So this will just be called acetic anhydride. Yep. Most of the time when you see anhydrides, they're going to be symmetric. Occasionally you see unsymmetric anhydrides, in which case it changes a little bit. So let's do another example. So this would be acetic acid. This would be, this should be a benzoic acid. This would go and form a new molecule that could be an anhydride.
Benzoic anhydride. Am I right?
This would be acetic benzoic anhydride.
That's like -2. That's -2.
You don't see these very often as reagents, but occasionally you see these unsymmetrical anhydrides show up as intermediates during a synthesis. So you just mush the two names of the acids together, couple them together as an anhydride, and change the ending from acid to anhydride.
Is it still like called mathematical?
Yeah. Okay, let's go on to esters now. And esters have a weird suffix. They have a new group. So I'll put that in brackets. And then blank 8. And again, I think these can best be explained with examples. Let's take a look at this compound. We have an ethyl group coming off where the carboxylic acid proton used to be. So this is an ethyl. What's this parent group called? Acetate. So when we name this, the conventional naming for this compound would be just ethyl first, because that's the substituent coming off the oxygen. And then the parent carboxylic acid was an acetate group. But let's do a couple other examples.
Okay. 2 words or 1 word?
It's 2 words. Oh, I forgot to turn off my...
Reminder, they're pre-registered.
Okay, so if we look at this one, we've got a group coming off the oxygen. What would this be? It'd be butyl. If this were an acid, what acid would it be called? Yeah, the chunk on the right that's circled in green. Pentanoic acid. So this would be pentanoate. So when we name this, this would be butyl pentanoate. So the first word for an ester is always going to refer to the group coming off the oxygen. The suffix is going to refer to the parent carboxylic acid, but we're changing the suffix to an 8. So we need to make sure that we fill it all in appropriately. All right, now let's go to amides. Oop. The suffix for amides is pretty easy to remember. We just change it to amide. So let's do some examples for these. Again, let's try to compare it to the parent carboxylic acid versus the new amide derivative. So we've got acetic acid. What do you guys think the amide is going to be called? Acetamide. Acetamide or acetamide, however you want to pronounce it. The key is that, again, we're going to be replacing the ic acid with the amide. And it becomes one word now. So let's do another example. This one gets a little bit tricky. Oh, sorry, let's break this down into the acid versus the amide. Okay. What's the parent acid called? Formic acid. All right, so that's the suffix.
Is it amide or amide? What are we looking to say?
What are selection things?
Formamide.
Really?
All right, but we're missing the beginning. We've got 2 methyl groups coming off of the nitrogen. So this is going to be called NN dimethyl.
What?
And what this refers to is we have 2 methyl groups off of the nitrogen.
So if it's one, it's just N-methyl.
If it was N-methyl formamide, we would only have 1 methyl group coming off of it. Does this look familiar to anybody?
No.
Yes.
I don't understand why they put N in.
They're both on the nitrogen.
Both methyl groups are coming off the nitrogen. It's to specify that the methyl group isn't coming off somewhere else on the chain, it's coming off of the nitrogen.
Why did you say N once?
Because that's implying that there are 2 methyl groups coming off of the nitrogens. If we had a longer chain, let's do another example where we can compare that. All right, so DMF is a common solvent in the lab, and it's the abbreviation for NN dimethyl formamide. Let's do one more example to go back to the other point. Actually, I'm going to move this over. Sorry. We'll avoid stereochemistry. All right. So let's try to name this one. You number from the carbonyl, because the longest carbon chain. 3, 4, 5, 6. So if we think about the parent acid name, what would it be called? Yeah, specifically it'd be 5-methylhexanoic acid, right? So this one would be N-methyl, 5-methyl, hexamide. So it's kind of a mouthful, but the 5-methyl refers to the methyl group coming off of the chain. The N-methyl refers to the methyl group coming off of the nitrogen. And so that's why we have the N designation now, is we want to designate the substituents coming off the nitrogen versus the parent chain.
Does it matter that N-methyl comes first than 5-methyl?
You usually see the naming with the N substituent at the very beginning, just to make it abundantly clear this is a substituent coming off the nitrogen. Yep.
After we start adding like chloros and stuff like that.
Yeah.
I'm not going to get too crazy into priorities and competing priorities, but we do want to compare substituents coming off the nitrogen versus the parent chain.
And it's hexamide, not
Wouldn't it be
hexanamide.
hexanum?
Thank you. This has been a really long day. I'm sorry, guys. Hexanamide.
Drop those 1 students.
All right.
I'm sorry.
So now let's go back to talking about the reactivity of these. Yep. Because we had 2 methyl groups coming off of the nitrogen, so we say NN. Yeah, I mean, oftentimes it's implied, but we still do NN. That's just the IUPAC rules. If there's 2 substituents, we do NN. All right, let's go to reactivity of carboxylic acid derivatives. So the easy trick is when you assess reactivity, you look at the Z. When examining reactivity, you want to assess whether or not Z would be stable as an anion.
Forgot your Y on reactivity.
Would be stable as an anion. All right, so let's go down that list. We already said we can make a chart. We can have one column be functional group, the other part be Z. And then I'm going to slide this over. I'm going to say pKa of conjugate acid. And what we're going to do is we're going to look at Z when it pops off and take a look at its conjugate acid. All right, so the first functional group, I'm going to choose acid chloride. So if we pop Z off and turn it into an anion, it'd be chloride minus. And if we do the pKa of HCl, the pKa is going to be -8. So chloride is incredibly stable on its own, right? It's more than happy acting as a leaving group. We saw that with SN2 reactions in particular. If we compare this to anhydrides, so we popped off this chloride, now we're popping off this whole anhydride group. That means that our Z group is going to be the acetate anion. And the pKa of its acid, which is acetic acid, is going to be 4.76. So it's still a good leaving group, but it's not nearly as good of a leaving group as a chloride, right? It's a lot less stable on its own. It still has resonance stabilization, but it's not as stable as hydrochloric acid or as the chloride ion. All right, let's compare this to our ester, where we can have our alcohol pop off as an alkoxide. The pKa, depending on the alcohol, is going to be roughly 15 to 16. So again, these are a lot less stable. When compared to acetic acid, why is it a lot less stable? Because no resonance, right? So in this case, it's not as good as a leaving group as an anhydride leaving group. And then if we compare this to amides, shoot, we can say the pKa is going to be about 38. So amides are actually pretty crappy leaving groups, to put it bluntly, which is good for us, right? Because our peptides, our proteins are made of amide bonds. We want them to stay together, right? We don't want our amide bonds breaking really easily, so amides aren't super good leaving groups. So if we're looking at all of these, we can explain the reactivity in terms of leaving group ability. And we can say that the better the leaving group, the more reactive they are. And specifically, this comes into play when we're looking at nucleophilic acyl substitution. So we'll go over this mechanism. All right. And in particular, we're going to do the basic mechanism first. All right, so let's say we've got our carboxylic acid derivative with a Z leaving group. We can react this with a strong nucleophile. So the nucleophile will add in to our carbonyl, pick up electrons. Our nucleophile attacks in. We go through this tetrahedral intermediate, and then what happens next? Yeah, the oxygen dumps down, kicks off Z as a leaving group. And so that's why I was saying you can view reactivity of these in terms of how stable Z is as a leaving group. The more stable Z is, the more reactive your carboxylic acid derivative is going to be. One thing that drives me nuts is I'm going to show you what I don't want to see. A lot of students get really tempted to show it like that. What's the problem with this? We're doing an SN2 substitution on an sp2 hybridized carbon. That doesn't happen. So we can't show it in one step. A lot of students get really tempted to try to show it this way, especially when they're in a hurry, but you have to show it going through a tetrahedral intermediate in order to be correct for this. One key thing is to remember with basic mechanisms, avoid positive charges. And that's really referring to your intermediate. So when we look at this mechanism, it's nice and simple. The nucleophile adds in, it's negatively charged, your oxygen has a negative charge, and at the end you end with the negative charge. We need to make sure that we keep track of this, especially when we switch into acidic mechanisms, because the acidic mechanism, we don't want to show negative charges on that. We only want to see positive charges. So now let's see nucleophilic acyl substitution under acidic conditions. And again, this draws on a lot of recent chemistry that we've seen. All right, so if we've got our carboxylic acid in an acidic medium, what's going to be the first step? Protonation. Because proton transfers are faster than all other sorts of chemistry. Thank you. So first step will be our protonation. All right, now we can have our nucleophile come in. Is our nucleophile going to be negatively charged if it's under acidic conditions?
Yes.
If it's under acidic conditions, you want to avoid negative charges, right? Positive charges are fine for acidic conditions, or neutral charges. So in this case, we're going to draw in our nucleophile as having its hydrogen on. It's just going to be neutral. Because under acidic conditions, it's not going to lose a proton, right? If we were under basic conditions, it could have a negative charge, but under acidic conditions, it's still going to have its proton. Okay. We've still got our conjugate base around, which can come and grab this proton really quickly once it's added in.
Would that be a negative charge?
Yeah, as long as your intermediates don't have negative charges, it's okay. But a conjugate base or water can come around and deprotonate. I'm fine with you showing it either way. Oftentimes these are done in water, so the proton transfers go through another nucleophile. So let's actually even change this, just to avoid that. Let's just show another nucleophile coming in. That way we avoid our negative charge on our conjugate base. Okay, so now we're ready to go. What do you think the next step is? Well, before we do that, let's try to turn it into an even better leaving group. We just protonated our nucleophile. So the Z can come grab a proton and reform our nucleophile. And I'll show you why here in a second. It does depend. With acid chlorides, you don't normally see that happening. Let's try to keep the conversations in the back a little quieter, guys. All right, so now we've got Z as a good leaving group. Can clamp down, kick off our Z, which is good because of most of the time we want to avoid negative charges. If we kicked off Z before, it would be negatively charged. Now we have our nucleophile in plus ZH. And then what do you think our last step is going to be? Deprotonation. So again, you could draw your nucleophile, lone pair coming in, deprotonating.
Is it okay though if you did the A minus?
It's okay. A lot of this depends on the specific Z group.
That's what I'm used to.
But this is the general mechanism. The key is to avoid negative charges. We have all positive or neutral charges here. So under acidic conditions, you want to avoid negative charges. And that was going to be my point. Under basic conditions, you can have negatively charged intermediates, and under basic conditions, you also don't want to see positive charges. All right, so I think we've got enough time to go through one practice mechanism. And this is one that's relevant to lab. And I chose this so that you guys could see what's going on. So in lab, many of you made benzoic acid in one of your early steps from acetophenone. And then you added in methanol. You added in catalytic acid. And then you got out an ester. What would the ester be called? Methyl benzoate, right? Because a group coming off the oxygen is a methyl group. The parent carboxylic acid was benzoic acid, so we'd say methyl benzoate. So now we need to go through and try to explain the mechanism for this. So the first step, you guys added in catalytic sulfuric acid, right? So our oxygen on our carbonyl can get protonated, dump off electrons. This makes our carboxylic acid a much, much better electrophile. Exactly. All right. Now we've got this, and we had methanol around in solution. Our homie. Never gets old. Kick up electrons. All right. Now we can draw our methanol doing a deprotonation. So the methanol oxygen can come grab its proton back from its buddy. So now we've got this crazy looking hydrate. We've got protonated methanol around. So now this one of these alcohols can come and grab a proton back from our protonated methanol. Okay, what happens next? Yep. And that's why we need to protonate our alcohol, is we don't want to have hydroxide get kicked off with a negative charge. Hydroxide's a poor leaving group, and we don't want to see negative charges. And we made water during this reaction. This water can come grab a proton, clamp down, and we can get to our final ester. This is an example of a reaction called a Fischer esterification. So it's a pretty simple process. You're going to have to practice a little bit of this with your problem of the day with arrow pushing. One thing I do want to go back to, because people were asking me about this in lab, was why are we getting the ester? Why is it not staying at the benzoic acid. And a lot of this comes down to Le Chatelier's principle with equilibrium conditions. So let's go back up to the overall reaction. If you look at your starting materials, you had benzoic acid. Did you only add one equivalent of methanol? You guys added a ton of methanol, right? You guys flooded the reaction with methanol. And so if you're thinking about Le Chatelier's principle says if you have more starting materials, you can drive the reaction to the product side. What happens if we had our product really, really wet with a ton of water in it? There you go, backwards. So somebody was asking, well, why does the product need to be super dry? Well, if you've got competing water around, it's going to lower your yield because it will actually push the equilibrium back to the other side. And there's a variety of ways to try to get around this in order to get quantitative yields of your ester. Does anybody know how we could drive this reaction to the product side exclusively? Take out water, right? And so there's actually a special piece of glassware where when you run this, you run it under reflux, and then the water will actually get trapped outside of the flask, and that's called the Dean-Stark trap. And what that does is it removes all the water and drives the reaction to completion. There's also these beads you can throw in your reaction mixture called molecular sieves, and they're these very porous beads that will only absorb water, not other molecules. And so in that case, it can suck all the water out of the reaction mixture, leaving behind only product. So there's a few tricks in order to get the Fischer esterification to work, but you're going to have to practice this proton transfer on your problem of the day. It's a little bit tricky. I know the rings are kind of strange, but do your best.